Hello, and welcome to EET3329C Communication Systems course at Valencia College for the fall semester of 2020. This is your lecturer, Dr. Wilfredo Rivas Torres. And if you've made it to this lecture, this is our very last lecture. We'll be covering lectures number 6, part 2 for digital data transmission. And again, congratulations if you have made it this far. Our topics for today will be digital carrier modulation and M-ary modulations. And specifically, we'll be talking about ASK, which is amplitude shift keying, FSK or frequency shift keying, phase shift keying or PSK, and quadrature amplitude modulation. So let's start by explaining what we mean by M-ary signals. So the binary baseband modulation that we've been seeing so far have one thing in common. They all transmit one bit of information over an interval of TB seconds, which is the same to say that we're transmitting at 1 over TB bits per second. Right? So that's our transmission rate. Um, if you want to send bits at a much higher rate, you can definitely make TB shorter, right? So we can go from 10 microseconds to 1 microsecond to zero point 0.1 microseconds, and you can increase your data rate that way, right? So if you want to increase your bit rate by a factor m, that means you reduce your bit time by the same factor m. However, nothing comes for free in this business, right? So the price that you pay is you need more bandwidth to do that, right? The faster you want to go with the shorter bit times, the more bandwidth you need, right? And bandwidth can be at a premium. Um, so fortunately for us, reducing the bit time is not the only way to increase the data rate. So a practical solution to this is to allow each pulse, remember we were having this, think about the rectangular pulse, or if you want to think about a pulse that's been with a certain pulse shape, you can think about that. But allow that pulse to actually carry more than one bit. And that is the concept that is called or known as M-ary signaling. So let's look at pulse amplitude modulation signals. We've looked at the single bit ones, but let's look at an M-ary one. So for each transmission, right, within the time interval TB, we want to carry more bits. But in order to do that, that means that we must have more than just two pulses, right? So by increasing the number of pulses to m in the signal set, we can then transmit more information per pulse, right? So let's look at this example of m equals 4, right? So in m equals 4 or a 4-ary system, we have basic pulses, which from now on I'll be talking about, if you hear me say symbols, it's still the same pulses as we had before, but because they carry more than one bit, the more common term in general in this field is to call them symbols. Even at the single bits, folks will still call them symbols, okay? So now think of a sequence of two binary digits can be transmitted by just one of these 4-ary symbols, right? And the reason for that is because you can take 2 bits, right, in combinations of 1 and zeros, and if you build up like a truth table, for those of you who've taken digital courses before, you know that there's 4 sequences, a total of 4 sequences you can have. So for example, we would have 1 1, 0 1, 1 0, and 0 0. Okay. Now, in this figure, we're showing the one possibility of a signal set that would cover what we want, what we're saying, right? So, for example, 1 1, 2 bits where in which a two-bit pair, which let's say 1 1 would have a pulse shape like this. It looks very similar to the one we've had so far. 0 1 would be just the invert the 1 1 pulse inverted. But look at 1 0. 1 0 kind of looks like the 1 1, but it has a different height, right? And the same thing for 0 0. Looks like the one for 0 1, but it has a different height. So there's your four pulses. They're distinct, and each one can carry 2 bits. What we're saying is we transmit this, and the receiver, when it sees it, it looks at what the amplitudes are, right? And it can determine, oh, if it has the positive smaller amplitude, it knows that it received 2 bits, and those 2 bits are 1 1. Okay. Um, Now we're going to change our again our nomenclature from to symbols, and now we say that each one of these pulses occupies a time ts or a symbol time. Okay. You can extend this concept of M-ary signals. Now you can think about 2 by 2 by 2, right? Every bit has two possibilities, right? So if you want 3 bits, there's each bit has two possibilities, so a total of 8 combinations are needed, right? You can go to 4-ary symbol set, excuse me, a 16-ary symbol set, not a 4, a 16-ary symbol set. So in general, right, if you have an M-ary symbol set, and they're always powers of 2, so let's not kid ourselves, right? That's why you see 2, 4, 8, and 16 so far. Um, and in general, an M-ary symbol set, right, it will have log to M bits, right? So if you want to know uh, how many symbols you need for the number of bits that you want to transmit at the same time, well, then that, in other words, you want to calculate your M, that is equal to 2 to the N, where N is the number of bits. Okay? So this means that you can increase the rate of information transmission by increasing M, which equals 2 to the N, right? Um, we should note that pulse amplitude is not the only, is only one of many possible choices for M-ary signaling. However, there's not that many choices that really give you an efficient bandwidth and power, while at the same time combating or making good use of the channel and sort of combating your noise, or trying to reduce the impact of the fact that there's noise. Eye diagrams are again a wonderful tool for this sort of thing. Here's an M level. Here's a 4 level or 4-ary system. Um, this is for a cosine raised cosine filter with a roll-off factor of R equals 0.5, as we saw last time. And you can clearly see where the sampling and decision instance is, right? The eyes are nice and open, and you can see where that uh, where the optimum decision sampling point would be, right? So digital carrier systems. So we talked about all the baseband stuff, right? That pretty much covers all the baseband stuff. So we know that baseband signals cannot go over a radio link or wireless channel. So because otherwise we need those gigantic antennas that we saw at the beginning of the course, right? So we need to go to a high frequency carrier system, right? Um, and we know that what we want to do is we want to shift the spectrum to higher frequencies, right? And by the way, the fact that we do this allows us to take advantage of FDM, right? Frequency division multiplex. So that's where we can have uh, more signal channels like on your TV, right? That when we say channels, we're not talking about the channel medium, right? Uh, In order to have more channels and implement FDDM, you have to have a large enough bandwidth of your channel, right? Hopefully you guys remember all that we saw earlier in the course. Um, so in digital carrier communication systems, you will all still need a modulator and a demodulator to transmit and receive the data, as we saw in AM and FM systems. Um, Now, in digital, the two devices, or the modulator and the demodulator, are commonly packaged together, and they call that a modem, right? For modulator and the demodulator, we call that a modem for two-way communications. Believe it or not, your cell phone is a modem. It actually has several modems because it can transmit and do different signals, right? Like Wi-Fi, Bluetooth, and your cellular communications, right? There's like three different modems inside of it. Um, so let's start talking about the different digital carrier modulation. And the first one that we're going to talk about is ASK, or amplitude shift keying. Okay? We know that in amplitude modulation, the carrier amplitude is varied in proportion to the modulating signal. Okay? Uh, and we can see what a non-modulated or unmodulated carrier looks like, right? That's like this waveform here. It's just a sine wave at a high frequency, right? Let's say we have a baseband signal that follows, our pulses follow something like this. Okay? In this case, the line code is either on or off, right? You have a 1 or a 0, right? You either have the presence of a signal, or you don't, to represent your 1 and your zeros, as we've seen earlier. Um, So when we take that and we multiply it by the carrier, we get our ASK signal here, right? Which is M of t times cosine omega ct, which, if you remember your AM signal, that's pretty much exactly the same way it looked like, right? Except that now our modulating signal actually turns on and off. Well, guess what? Well, that's exactly what it's going to do to your carrier. When you multiply this by the carrier, it turns the carrier on and off, right? And that becomes your ASK signal. Um, and this is a modulation scheme. We can transmit binary data. Notice this is not M-ary yet. So we can transmit binary data this way. Actually, this sort of transmission is known as on-off keying as well. And in the field, you will hear both of them. Some people just more people prefer ASK than OOK, right? For the obvious reason, but the OOK kind of connotations, right? But you do hear both of them in the field, right? And you can use different pulses. They don't have to be rectangular. Again, they can be pulse shapes by a cosine filter, for example. Uh, Now, if you do that, you generate an ASK that doesn't have a constant amplitude. You notice here that by using these rectangular pulses, your ASK signal has a constant amplitude. Okay. All right. So, nice. There we go. So now let's talk about digital carriers, the PSK. All right. If the MFT, your message signal now, still digital, but now it's a polar signal, right? Has both positive and negative. So a plus one signal will represent a binary one, and a minus one will represent a binary zero, right? That means that when we modulate our signal, right? We try to modulate our signal. What you end up with the one being a PT, cosine omega CT, and the zero being minus PT cosine omega CT. And we've seen that this minus, we can convert it into a phase, which is plus pi, right? So now you have two pulses that only vary by pi radians apart in phase. So the information does reside in the phase or the sign of the pulse, either way you want to look at it. And therefore, we call this phase shift keying or PSK. Notice the transmission is still polar, right? You have two distinct signals, right? Um, so what ends up happening is that, in fact, what ends up happening is just like ASK, the PSK chiromer has exactly the same form, right? If you look at ASK, right, it has this form. This is the same form for the PSK, right? In fact, I made the mistake here that I still call it ASK, but this should be a PSK, right? So I'll correct that in the final slides for those of you that are taking the class. Um, the only thing here is that your AAK here has different polarity, right? And look what it does to the signal, right? So here's A, and notice the change of phase. It goes exactly 180 degrees, right? And then every time you have a bit change, you can polarity change, not a bit change, a polarity change. You can see that the phase of the signal also changes, right? And this is what it looks like. Okay, our third digital carrier modulation is known as FSK. Um, so when the data is transmitted by varying the instantaneous frequency, this is what we call frequency shift keying or FSK. And that's what's shown in figure C here. Notice that you have a certain frequency during this pulse, but when the pulse changes to 0, you have a different frequency. Right? And that's what FSK does. It's constantly switching between the two different frequencies. And that's how we encode our information and frequency, like we did with regular FM. Right? So the 0 is transmitted with a certain frequency, omega Z0, and the 1 is transmitted with a certain frequency, omega Z1. Um, You can also view the FSK signal as two alternating ASK signals. Uh, Once you know learn ASK, the other two kind of fall logically if you guys have been following. Actually, they all kind of fall off logically. Even quantum falls off logically off of ASK. Um, so we can use an expression like this. Again, it looks very similar to the ASK, except that now you have two terms because you have two different frequencies, right? Um, And again, the FSK signal is just a superposition of two ASK signals. It's just that the pulses are different, right? You have two different pulses, and therefore they generate two different frequencies. Okay. Um, so we haven't mentioned the frequency domain yet today. So why don't we go ahead and move into that? All right. So we know that for ASK, right, for the amplitude modulated signal, what we do is we're going to take the baseband signal and it's going to be shifted onto the carrier plus or minus FFC if that's the frequency of the carrier, right? And here we are only showing the positive side of the frequency spectrum. You guys know that on the negative side, there's a copy of this, right? So this is what it kind of looks like when you look at the ASK signal, like what you see here. Um, Notice that for the ASK signal, there is a DC component in the signal, right? Therefore, at the carrier, you will see a component there. You actually see a a spike right in the middle of your spectrum. That is correct, and you would see that if you look at this on instrumentation like a spectrum analyzer, you would actually see that. Um, Now the PSK signal also kind of fit the same description, and you have the same power spectral density. It does the same thing at plus or minus FC, but because it's polar, it does not have a DC component, and therefore it does not have a carrier in the middle. So this is like when we were talking AM suppressed carrier, uh, but notice that ASK does not suppress the carrier. Okay, so one has the carrier, the other one does not. Other than that, they're really hard to tell apart. If you don't, if you can't see the carrier for some reason in your instrumentation or something, modulation index is just not right or whatever, you might not see the carrier, then it's really hard to tell them apart. Okay. Um, Again, the FSK signal can be viewed as two interleaved ASK signals. Um, it's just that now you have two baseband terms, one for 0 and one for 1, right? And they are non-overlapping in time. Um, So you have a power spectral density that's the sum of two ASK signals. It's just that because they're at different frequencies, right, you end up with a power spectral density that looks something like this. Notice that again, it's like the FSK, except that now you have two distinct frequency, right? Your FC0 and your FC1, right? So what ends up happening for FSK is you end up with two humps, if you will, or two peaks in the frequency domain. Um, Now, it can be shown that by properly choosing FC0 and FC1 and by maintaining phase continuity, right? And let me go back and talk about what their meaning is when by phase continuity. See, when you go from the 1 to the 0, there's nothing that disrupts the signal, right? If you see any discontinuity, right, or some kind of change like you do with PSK, this is a discontinuity in phase, okay? If you eliminate that for the FSK, then we can show that, where was I going? Oh, that there is no discrete component, i.e., what that means is you suppress the carrier, both FC0 and FC1. Okay. Now, for the same data rate and everything, and if most things are kept the same, FSK is always occupies more bandwidth. It's always a wider bandwidth. And it should kind of come logical to you, right? You have two frequencies, you have the same baseband power spectral density, but now you're putting them on two different carriers, if you will, right? And that's for the two-ary system. All right. Or for the binary system. Okay, so M-ary, digital carrier modulations, right? We can also uh, do M-ary modulation with digital carriers, right? Um, So we will apply the M-ary signaling at the baseband, and then we would have M level ASK, so several levels, not just on and off anymore, or simple on and off. You'll have an M frequency FSK, you have M carriers, or M phases PSK, and then we are going to talk about M-ary QAM. So just hold on a little bit, but it too can be M-ary, right? It's just that it's easier to discuss QAM, right? What this QAM is once we understand a little bit more about these other M-ary signaling formats. Okay, so let's talk about the ASK one first. So the binary ASK is actually a part of a larger group, right, of M-ary ASK signals. Actually, all the binary ones are, right? So you start off with saying that the signal is equals 0 for a 0, and we started saying it was A cosine omega c t for a 1, right? In an M-ary ASK, where you can send log 2 of the M levels that you have, bits at a time, then you need as many different signals. So because the information is contained in the amplitude, that's really the number of amplitudes that you need. Notice how we say 0A, 2A, all the way to M minus 1A. So these are the different amplitudes that you have, okay? And remember, this is still an AM signal. It's just that it has M discrete amplitudes, and everything is at a modulation index of 1, okay? Um, the bandwidth remains the same as the binary ASK, while the average power increases. So sure, we are sending more information in the same uh, bandwidth, and we're sending it in the same time, right? We're sending 2 bits in the same period of time, let's say, right? So TB equals TS, right? So you'll keep the bandwidth the same, but you have to pay the price somewhere and you pay it in power. You have to increase the power by this expression here, m minus 1 times 2m minus 1 divided by 6, right? And again, the modulation, like we saw for AM, is achieved via envelope detection or coherent detection, okay? We already discussed those, no need to discuss those again. FSK, um, we know that we do that. We're going to generate a series of carriers, right? Different carriers, in a certain particular pattern for log 2m bits, right? Um, so generally for FSK, we design a frequency increment. So each symbol has a different frequency, and as we go from one symbol to the other, we have an increment in frequency, right? I'm going to use the nomenclature F underscore INC for F increment. The book uses this delta F. I do not like it, so I got rid of it. I feel that it's a little bit clearer using F increment. Okay, I can't use delta F because delta F obviously we already use in FM, and we want to keep the same definition so we don't write as much as possible, right? So we need to create a series of M frequencies, right? So F of lowercase m. This is your formula. You start with the first frequency and then m minus m, whatever m is, minus 1 times the increment gives you what the new frequency for the next symbol is. And you're going to need m, capital M of those, right? Where m is the order of your M-ary system. So if you have an order of 4 for a 4-ary system, m would be 4, right? How much is the frequency deviation, right? That's always or the total frequency deviation. Remember, that's the frequency deviation. Like an FM, we said, oh, our frequency deviation depended on the peak of the signal. You guys remember that, right? And then you had a certain delta F that we multiplied by the K of F, right? It's the same concept, the same delta F, except that here, how much is that? Well, it's FM or F of 4, if you want to put it there. If it were a 4-ary system, it would be F of 4 minus F of 1 divided by 2, which is the same as 1/2 of m minus 1 times the increment frequency, right? Um, Now, the set of FM frequencies that you select determines the performance and the bandwidth of the FSK modulation. So FSK is it takes a little more than just, okay, let's put it on the carrier, right? You have to be very careful how you select these frequencies, right? Because if they're choosing too large, then the FSK system will occupy too much bandwidth. Now, if you choose them too small, then over time, right, over the symbol interval, the different symbols will virtually show no difference. They're very similar one to the other, and you'll be unable at the receiver to distinguish the different FSK symbols. What this further implies is that a large increment in frequency you're wasting bandwidth, which is always at a premium. Where if it's too low, then it's prone to detection errors due to noise and interference. Okay, and we know that the whole game in digital communication is about reducing the detection error. You always want to, if you send a 1, you want to detect the 1. If you send a 0, you want to be able to detect the 0. Right? So it's all about reducing the detection error. So an FSK is very important how you select your frequency increment. Um, If you can design the FFK symbols to be orthogonal, remember when we talked about orthogonality? One of the nice properties of orthogonality is they don't interfere with each other, right? And they'll be distinct enough. They're just different. They don't interfere with each other, right? Um, so if you can make them orthogonal and small, in a small f increment, then the signals will be truly distinct over their interval and the bandwidth consumption will be small. So how do we make them orthogonal is the question. Well, somebody already solved this for us, right? And in order to make the orthogonality condition is you make the increment 1/2 times two times the symbol time, right? Whatever the symbol time is, which is the same as 2 times the bit time times log 2 of m, right? Now you know what the relationship with TS and bit time is. TS is 2b times log 2 of m, right? So this choice of minimum frequency separation is what's known as minimum shift FSK, right? And you'll hear that term a lot, minimum shift FSK. Okay, you can use other frequencies, and you might occupy too much bandwidth, but hey, it'll still work. Or you make them the increment too small, and you open yourself up to problems with interference and noise. But hey, it might still work depending on what you want. Now, if you want to make sure you have the most optimal thing that you can think of, then you use the minimum shift keying and you make the frequencies orthogonal. All right. Now, if you use minimum shift FSK, this is your delta F based on this F increment, right? And then it's a FM signal, so the bandwidth is according to Carson's rule again, which is 2 delta F plus B, if you guys remember that. Which reduces down to this formula, m plus 3 over 2b log 2 of m. Okay. In general, the bandwidth of an orthogonal M-ary scheme is still m times bigger or wider than the binary scheme, right? Um, the rest of it is sort of the same things we've been talking about. The communication rate increases by a factor of log 2m. Remember, it's at expense of bandwidth. Uh, for a comparable noise immunity, the transmitter power is practically independent of M. That's a nice thing about FSK, right? It has all this bandwidth restrictions, but when it comes to power, it's a wonderful thing. It's what we call a constant envelope signal, right? Same as regular FM. It has always the same amplitude, right? So increasing the data rate, you don't have to increase the power of the signal, which is always a kind of a really nice thing, right? Um, However, the bandwidth again is required to increase when you linearly increase the value of m. Now, we're going to talk about M-ary PSK, and we're going to sort of flow into what QAM is, okay? Um, and this is the basis of a lot of our modern day digital communications. Here's the basis. Here's a base of a lot of that. Um, And we start off by saying that in general, a PSK signal has this sort of a form, right? This sort of a form, where A of M is A cosine of the phase, right? Um, you can disregard for now the square root of 2 over TB. That's nothing but a constant that affects the amplitude, and we can absorb that elsewhere. But they do that for keeping the energy and stuff like that consistent throughout the waveform. It's really not that important. What is important is this A of M and B of M. Notice that the difference is just that you have this minus sign. One is a sine and one is a cosine, so there's a 90-degree difference already, and then one has a minus sign, right? We can define a two-dimensional space based on this, right? So notice that we started talking about cosine omega c and sine omega c of t, right? And if you look at it carefully, we end up with a function with a representation of ASK that looks like this. And you have these two basis function where one's a sine and one's a cosine. Now, if you think of it, if we go back and we start to think of it as a vector, right? A vector, anywhere in the space, you always have a real part and an imaginary part. Think about as A of M psi of t, that's the real part, and this is the imaginary part. All right, or you can just think about it as a vector on a Cartesian space, right? This is the component along the x-axis, and this is the component along the y-axis. In common practice, we talk about it in terms of complex numbers, right? Uh, That way we can do magnitude and phase or real and imaginary. Right? All right. And you'll start seeing some of these equations begin to look like that in a little bit here. Um, so there is a special requirement that the ASK signal must meet. And here's where the whole thing about complex numbers or XY coordinate systems starts to play. A squared plus B squared equals A cosine square plus minus A square sine square, right? And if you notice, that's kind of the equation of a circle. And then what all this results in is a constant amplitude of A square, okay? Um, that is, all the signal points must stay on a circle of radius A. That's what that means. So for PSK, okay, all these points that I was talking about, either real and imaginary or Cartesian coordinate, doesn't matter which way you want to look at it at this point. Even though I encourage you to look at it as real imaginary, which is what I'm going to continue to do from this point on. Um, Everything should fall on a circle of radius A, right? Um, in practice, all the points are in the M-ary PSK are chosen to be equally spaced on this circle. So those, therefore, your phi of m, the theta of m, so, or the phases, you start off with some offset, and then 2 pi over m, m minus 1. Those are be the different phases of the different pulses that you're going to use for your M-ary PSK signal. So this is what we're talking about. So for BPSK or binary PSK, right? That's what the B stands for, binary. You only have 2 points, right? You have one at A and one at minus A. Notice they do lie on a circle of radius A, right? So this is a, if I would call this, I could call it a two-ary system. We just call it a binary, right? There's a quaternary where quaternary stands for 4, or M equals 4. There's a four-ary system. And notice that now there is a certain theta 0 at the beginning, but then again, all the points are equally distant from each other on this circle, and they all, of course, fall on the same circle. And the same thing with APSK, and you can see how we can extend this. Right now you have APSK, and this is how the APSK would be. Right? Notice that in the APSK, we started with a phase of 0. That is not a requirement. It could have started off with a phase, let's say here, as long as they're all equidistant from each other. Yeah, so you can kind of see that rotating. Depends on what you need or what your starting point is. Okay. These are ideal constellations. That's what we call these. These are called constellations, right? And you can measure these constellations for your modulations on different instrumentation, right? Actually, the instrument that does this is normally called a vector signal analyzer. All right. So we will further generalize PSK. So what happens with PSK? PSK is really like a, you can think of it as a special case of quadrature amplitude modulation, or QAM. Now, um, so QAM, what QAM does, it gets rid of the requirement of PSK to have constant magnitude. So it gets rid of everybody having to fall on a circle. That kind of throws it out the door. I don't really need that anymore, right? So the much more general QAM signal format can be used for any kind of, for digital modulation as well, right? And the signal looks like this. Now you have to look at it carefully. Now notice that you have an A of I times P of T and a B of I, whereas before these were sort of fixed numbers, right? Fixed quantities because they had to have the constant amplitude, right? Um, And we can also express it instead of real and imaginary, right? A of I and B of I. You can actually represent it as magnitude R of I and phase phi of I. And this is how those numbers relate to each other, right? And remember, your P of T, the pulse, can be a properly shaped baseband pulse, right? Like a raised cosine filter, okay? Um, One of the big things about Quam is the easy that it is to both generate, right, or modulate and demodulate. In fact, the modulator and the demodulator look very similar. So we are going to call our real and imaginary signals M of 1 and M of 2, right? I could have called it I and Q, where I stands for in phase, right? The in phase component, which is M1, and the quadrature component, which is M2. Sometimes we just call them I and Q right off the bat, right? So I stands for in phase and Q stands for quadrature component. Okay, you feed those to this combination of a circuit, which it's kind of not that complicated, right? You have an oscillator. You need to shift the phase by pi over 2 and feed that to one of your multipliers times the quadrature signal, and then the oscillator goes straight to the multiplier with no phase shift, and then that multiplies the in phase or the I value or the I component. You add them together. This is stuff that you want to transmit. This is stuff you put on the uh, feed your antenna with, goes over the channel, and then you demodulate it, and the demodulator looks so similar, it's identical to the uh, modulator. I know there's a two here, and most textbooks do the two thing to say that they're conserving energy when you put the equations together, et cetera, et cetera. The equations are not that important. It's and just remember, if you're low in amplitude or something, you can always put amplifiers, put gain. The important thing here is look how similar the two are. And of course, you need the low pass filter on the receive side. We've always seen this. Um, and then you get back your in phase and your quadrature components. Okay. If we were to look at the constellation of the Quam signal, um, right? Well, sorry, I'm jumping a little bit ahead. Um, so one popular choice for M and a quantum system is 16. We call that 16 quam. Not surprising, right? We would call it 16 PSK if it was PSK. Well, 16 quam. That means you have a 16 ary pulse signal set, or M equals 16, which means in log 2 of 16, you have 4 binary digits. Um, uh, Therefore, there are 16 combinations, which is what we're seeing here in um, figure B of 638b. So we're looking at the constellation of a 16 quam, right? And we should see 16 dots. Again, this is the ideal constellation. In the real world, there's noise, there's distortion, so things move around a little bit. But as long as you are, and again, there's all kinds of studies just sort of beyond the scores. But as long as you're in a certain region around this, you can definitely tell that it is this symbol, right? If it strays a little too far where it's right in between this symbol and this symbol, then you can kind of, which one is it, right? But as long as, and there's, again, there's all kinds of theories for this, and the likelihood receivers and the like, and we'll, that's again for another course. Um, the nice thing about this, right, compared with binary PSK or BPSK, the 16 quam system bit rate is quadruple without increasing the bandwidth, right? That's one of the advantages of going to this M-ary systems, right? You get that modulation efficiency out of it, right? Where the modulation efficiency is pretty much M. Um, you can increase M, and people have gone crazy with these quam. So there's a 4096 quam. Some of the modern day Wi-Fi systems use that. I haven't kept up with 5G, but I think 5G uses a very high level of quam, but I can't be for sure. Okay. And that's about it. So remember, from the knowledge, all the receiver has to do is at the end of the day, figure out what the values of the I and Q are, and based on that, it knows which symbol set it is, right? Which one of the symbol sets it is, and therefore it knows which bits were transmitted, right? And that's all the demodulator has to do, or the receiver has to do after demodulation does it know. All right, so the decision is fairly simple. Uh, okay, so that's about it for the course. And I'll hopefully see some of you in a future course. If not, very good luck to everybody. And thank you so much for attending the course.